Hi, this is a video tutorial for Meander Migration Modeling in the iRIC platform, and this is video number 9. It's entitled Modeling Cutoff. A first example: chute cutoff and upstream and downstream cutoff locations. In this tutorial, I'm going to use an example from the Sacramento River, in the upper part of the river, near River Mile 190. And I'm going to start with the center line from the year 1966. This is just really convenience that I'm using this. It's one that I have been using. It's handy, it's effective. And although my model actually runs through the year 2016, the story that I'm telling you ends in the simulated year 1967, when the simulated cutoff occurs. This tutorial is going to be the first one that describes the Meander Migration Model and how it's used to simulate cutoffs. And as I will mention more than once, this cutoff capability is what we call a rule-based function. We're not exactly sure how and why cutoffs do occur. The processes causing cutoffs are pretty complicated, and we're not going to go into those theories here. And we base the migration model's ability to model cutoff on how we observed that bends actually cut off. So we built the model so you could specify how you want the cutoff to occur. Now the meat of this tutorial is going to be to how to use the upstream and downstream cutoff location points. Okay. In the iRIC model, you go to the calculation condition and then the settings, and you get the calculation condition dialog box brought up. Everything's going to stay the same in that dialog box as it was set up for our last tutorial, except that we're going to invoke the cutoff parameters dialog box. And of course, make sure that you change your output location as I do each time I run the model. But the new factor here that we're going to deal with is the cutoff dialog. When you open the calculation condition dialog box, you go to the cutoff parameters section. When you go to that, it'll look something like this. Now I'm going to walk you through what you want to do to set up this dialog box. Of course, this is just our test. You're going to have to ultimately choose your own parameters for your individual river. And as is quite often the case in these tutorials, the parameters we're going to use, and those that we actually have set as default values in the code, are ones that work well on the Sacramento River, which is our go-to test case all the time. The first distinction that we make, which is really somewhat arbitrary, but it's very useful nonetheless, is that there's a distinction between a neck cutoff and a chute cutoff. We don't tend to go into the theory in these tutorials, but in the simplest terms, a neck cutoff is one that occurs when one limb of the meander bend gets so close to the channel on the other limb that the two channels touch. In other words, the neck narrows down, that's why it's called a neck cutoff, and closes, so to speak. And so in real life, when they get, really pretty close, the water flows over and there's a cutoff. In the model, when we model neck cutoff, when the upstream and downstream limbs touch, the neck cutoff occurs. So we're not going to be using that neck cutoff part in this tutorial. We're going to focus on the chute cutoff. In the case of a chute cutoff, the bend cuts off before the channels touch, sometimes significantly before the channels touch. The water travels across the land in the center of the bend, which is a so-called chute, and causes a cutoff there. On the Sacramento River in California, this is what happens really nowadays. So we've given a lot of good modeling space to that particular situation. Okay. In the dialog box for the neck cutoff algorithm, disable the neck cutoff routine. And under the chute cutoff algorithm, enable the chute algorithm. So here you see that. The neck cutoff algorithm is disabled. The chute cutoff algorithm is enabled. Then set the values that you see here, which are probably already there as default values. And again, I'm not going to explain the rationale for these. We'll leave that for another time and place. Again, suffice it to say that these values work well on the Sacramento River. First, we have a choice of what will control the chute cutoff. So in this example, we choose sinuosity only. The other values I'll explain in a minute, or at least describe that we're going to put them in, but go down to the bottom where it says cutoff recurrence interval. This is only used when you're using the variable flow algorithm, which we are not in this case. And the rationale for setting it to 0, well, the rationale for using this particular possibility is that the cutoff won't occur unless there's water going over bank. So this gives you the flexibility of specifying what the recurrence interval is that occurs when it goes over bank. Again, we're not going to use that particular one in this tutorial. Okay, the other values we will set as they're shown here. The bend distance threshold is grayed out because we're only enabling sinuosity only. So, you set the sinuosity threshold to 1.8, you set the upstream sinuosity factor at 0.25, you set the downstream sinuosity factor at 0.1. And to repeat, then your dialog box will end up looking like this. Okay, here's the location I'm going to be using. It's rather an uncharacteristically sinuous bend on the Sacramento River. It's one that we sometimes call the duckbill bend. And it was easiest for me to pull up a recent photo here, which is roughly 2016. So when you see the beginning channel, recall that I'm using 1966. It's not going to match the channel in the photo exactly, but don't worry, I know that. I'm just doing this for convenience, and I'm trying to show the model. And the photo gives us some good context. Model doesn't run off of photos. The model runs off of the center lines. So the photos are background pictures. Useful, but not what the modeling is run from. Quick review here. This rule-based approach is pretty much you tell the model what you want it to do, it'll do it. And again, our example will start with the 1966 center line, and the modeling only gets as far as 67 because the bend is greater than 1.8 sinuosity. You know, on the ground in real life, this bend is restrained, and it hasn't cut off as of 2017. But because it's a good model, and it's modeling, we can allow the bend to cut off, and it's a very good example to show how it works. So here we go. The blue line is the 1966 center line, and this green one is where it cuts off with the default parameters that we have put in. As I said, it cuts off in the first year, so that's the simulated 67. Now, the beginning place, the upstream place where it cuts off, by the way, upstream is the top of your screen, downstream is the bottom of your screen. You'll see that those beginning places, both upstream and downstream, are unnaturally sharp. But after the model runs for a few years after the cutoff, they smooth out. I'll show you that. Now that's, the red line is roughly 10 years after the cutoff occurs. Okay. Now I'm going to show you how adjusting works for the upstream and downstream cutoff location parameters or factors. First of all, we're going to start with adjusting the upstream parameter. Slide I just showed you said downstream, but that was incorrect. This is the upstream factor that we're adjusting, and the pinkish line is the cutoff location when the upstream factor is set to 0.5 or 1/2. And you can see it cuts off farther upstream than when it's set to 0.25. What exactly does this mean? Well, the best way is just to continue to show you these. It chooses how far upstream to go from the inflection point for the cutoff to initiate. So when you have the default of 0.25, it means that the program looks at the bend immediately upstream from the bend we're interested in, and then goes a quarter of the way upstream from the inflection point between the two bends. Now the inflection point is where one bend stops and the other one begins. It's where curvature goes to zero, where one curvature would be kind of a positive curvature, the other one a negative. So it's when it stops curving in one direction and starts curving in another direction. That's the inflection point. So again, 0.25 means that the program looks at that bend upstream from the one we're interested in and goes a quarter of the way upstream from the inflection point between the two bends. Okay, to complete the upstream demonstration, I'm going to set the upstream factor to 0, and here you see it. Bingo! Yellow line is where it will cut off with the upstream factor set to 0. Again, because this is a rules-based part of the tool, you're going to have to look at historical cutoffs in your own system and get a sense of where they cut off. A really good first estimate for the Sacramento is 0.25, that the green line that we have here. Now I'm going to show you how the downstream parameter works. It's the mirror of the upstream, and again the best way to describe this is just to show you. In the downstream case, it chooses how far downstream you go from the inflection point for the cutoff to connect with the downstream bend. And here's the cutoff with default values again, 0.25 upstream and 0.1 downstream. Okay. Again, the default 0.1 in the downstream direction. It looks at the bend immediately downstream, then goes 1/10 of the way downstream from the inflection point between the two bends. Now we'll change the downstream factor to 0.5. Before I do that, take a look at that downstream bend. It's kind of a long, loopy bend, so changing it to 0.5 gives you something a little unrealistic, but we're doing it to show you how the model works. Okay? Now, say the light blue line here shows the connection point downstream if the factor is set to 0.5 or halfway through the downstream bend. And now to complete this demonstration, we're going to change the downstream to 0. And that is the orange line. That's where it would go in the downstream direction if it was set to 0. Okay, that's it. That's really all you need to know to get started modeling cutoffs using the Meander Migration Model. And an overview, in summary, this tutorial is the first of a couple that are going to show you how you can simulate a cutoff using this Meander Migration Model. And as I've stressed, it's a rules-based model. It's really cool because it does all the work for you. It models the channel migration up to the point of cutting off, and then it models the evolution after cutoff, and it lets you specify how it cuts off, why it cuts off, and in this case, because the sinuosity was greater than a certain value. It's important to remember that you're the one that's specifying when the trigger's pulled, based on rules, not based on first principles. And in this particular case, we specified that the bend had to have a sinuosity greater than 1.8 before it would cut off. And then we tweaked where the cutoff commenced and where it ended. And the meat of this one was really showing you how the upstream and downstream connection point factors worked. As usual, don't hesitate to contact me if you have any questions about this, and thank you for watching.